In mathematics, there are thousands and thousands of theorems, but the one theorem that anyone who's been to school knows is the Pythagorean theorem, and that's the theorem that expresses the relationship between the sides of a right triangle. The theorem is named after a famous ancient Greek philosopher, Pythagoras, who lived from 570 BCE to 495 BCE, and that's 2,500 years ago. He's also known for the Pythagorean tuning in music, the 5 regular solids in geometry, the theory of proportions, and other mathematical and scientific discoveries. He is believed to be the first to teach that the Earth is a sphere. Pythagoras' philosophy lasted well over 1,000 years. The shape of a screen depends on what is called the aspect ratio, and that is the ratio of its width to its height. The two most common aspect ratios are the wide screen with aspect ratio 16:9 and the full screen with aspect ratio 4:3. The 4:3 ratio was the standard for filming early movies and influencing the manufacturing of television and computers. However, the current standard for a high-definition television is a 16:9 ratio. Later on, we'll use these ratios in some problems involving the Pythagorean theorem. You will recall that the sum of the 3 angles in any triangle must be 180 degrees. Now suppose we have a right triangle ABC with the right angle at A. Which of the following is always true about angle B? It's between 0 degrees and 90 degrees, but not including 0 degrees and 90 degrees. It's equal to 90 degrees. It's greater than 90 degrees. We know that the sum of the remaining 2 angles must be 90 degrees. So angle B plus angle C equals 90 degrees. Now, if angle B is 90 degrees, that makes angle C 0 degrees, and therefore we don't have a triangle in the first place. So that rules out option B. If angle B is greater than 90 degrees, that will make angle C negative, but all the angles are positive here. So that rules out option C. So we conclude that option A is the correct option. We conclude that angle B must always be between 0 degrees and 90 degrees. In fact, the same is true for angle C. The answer is option A. And what we get out of this is that in a right triangle, the 90-degree angle is the largest angle. The side opposite the right angle is always the longest side of the triangle. It is given a special name. It is called the hypotenuse. The 2 smaller sides are called the legs of the triangle. 2,500 years ago, Pythagoras drew squares on the sides of a right triangle to examine the relationship between the side lengths of the triangle. Firstly, he drew a square with one side the hypotenuse of the right triangle. Secondly, he drew a square such that one side of the square was the smallest side of the triangle. Then Pythagoras drew a third square such that one of its sides was the remaining leg of the triangle. Pythagoras discovered that the areas of these 3 squares were related. Did you notice that the 5 pieces that made up the smaller 2 squares also fit perfectly inside the larger square? This tells us that the area of the larger square is the sum of the areas of the 2 smaller squares. The result can be expressed as the Pythagorean theorem. It says, for a right triangle, the area of the square of the hypotenuse is equal to the sum of the areas of the squares on the other 2 sides. Example 1. The areas of the squares on 2 legs of a right triangle are 8 square centimetres and 12 square centimetres. What is the area of the square on the hypotenuse? Well, let capital A represent the area of the square on the hypotenuse of the right triangle. By the Pythagorean theorem, A equals A plus 12, which is 20. Therefore, the area of the square on the hypotenuse is 20 square centimetres. Example 2. The square on the hypotenuse of a right triangle has an area of 34 square centimetres. The square on one leg has an area of 16 square centimetres. What is the area of the square on the remaining leg of the right triangle? Well, let capital A represent the area of the square on the remaining leg of the right triangle. By the Pythagorean theorem, we have that 34 equals A plus 16. Now this is an equation, and we know how to do equations. We just subtract the 16 from both sides, so that will be 18 equals A. Therefore, the area of the square on the remaining leg is 18 square centimetres. We can express the Pythagorean theorem using algebra. In any right triangle where C represents the length of the hypotenuse and A and B represent the lengths of the 2 legs, C squared will be the area of the square on the hypotenuse, and A squared and B squared will be the areas of the squares on the 2 legs. Then the Pythagorean theorem gives us the following formula: C squared equals A squared plus B squared. Let's do 2 basic questions to illustrate how the Pythagorean theorem is used. Question 1. The length of one leg of a right triangle is 8 metres, and the length of the other leg is 11 metres. What is the length of the hypotenuse? Round your answer off to 1 decimal place. Well, since the triangle is a right triangle, we may use the Pythagorean theorem. So we'll let the length of the hypotenuse be x metres. So by the theorem, we have x squared equals 11 squared plus 8 squared. So that's 121 plus 64, which is 185. So x will be the positive square root of 185. X is positive because it represents a length. That will give us x equals 13.6014 and so on. We round that off to 1 decimal place, we get x equals 13.6. So the required length of the hypotenuse is approximately 13.6 metres. The second type of problem, which involves the Pythagorean theorem, is the situation where you're given a right triangle and you're also given the length of the hypotenuse and the length of one of the legs, and you have to find the length of the other leg. Let's look at question 2. A right triangle has its hypotenuse 17 metres long and one leg 12 metres long. What is the length of the other leg? Give your answer to 2 decimal places. Well, let the unknown length of the leg be x metres. And since the triangle is a right triangle, we may use the Pythagorean theorem. And that gives us 17 squared equals x squared plus 12 squared, and this is an equation. That's 289 equals x squared plus 144. We subtract the 144 from both sides and we get 145 equals x squared, and so x is the positive square root of 145. We know that x is positive because it represents a length. That by the calculator gives x equals 12.04159 and so on, and rounds off to 12.04. So the second leg of the triangle is approximately 12.04 meters long. The triangle is almost isosceles, but not quite. Now we can go back and look at the computer monitors and the television screens that we talked about before. Consider the following. In an electronics store, two computer monitors are both described to have 19-inch screen, but their rectangular shapes are not congruent. Retailers list the sizes of computer monitors and televisions as a single number. How are the sizes of computer monitors and televisions determined? The sizes of monitors and televisions are described by the length of their diagonals. The width of monitor 1 is 16.4 inches and its height is 9.2 inches. Monitor 2 has a width of 15.2 inches and a height of 11.4 inches. How would you calculate the size of each monitor using the given dimensions? Let h represent the length of the hypotenuse of a right triangle which we imagine is on the screen. Now h is a positive number because it represents a length. By the Pythagorean theorem, we have h squared equals 16.4 all squared plus 9.2 all squared. We square that and add them together and we get h squared equals 353.6. Now we take the positive square root here because we know that h is a positive number, and so we get 18.804 and so on. Therefore, the diagonal of monitor 1 has an approximate length of 18.8 inches. Let's have a look at monitor 2. Let K represent the length of the hypotenuse of a right triangle which we imagine to be on the screen of monitor 2. By the Pythagorean theorem, we have that k squared equals 15.2 all squared plus 11.4 all squared, and that expands out and adds together to give 361. So we take the positive square root and we get k equals exactly 19. Therefore, the diagonal of monitor 2 has a length of 19 inches. So even though monitor 1 and monitor 2 are different shapes, they are both 19-inch monitors. Remember, for monitor 1 it was 18.8 and that would round up to 19, so it would be a 19-inch monitor. Example 3. The length of the hypotenuse of a right triangle is 25 centimeters and the length of one leg is 7 centimeters. What are the perimeter and the area of the triangle? Well, what we do here is to draw a diagram. So we draw a right triangle and we put the information on. That's the hypotenuse is 25 centimeters and the shorter leg, we'll write that as 7 centimeters, and we'll let a centimeters be the length of the missing leg and we'll write that on there too. Since it's a right triangle, we can use the Pythagorean theorem, and that can be represented as c squared equals a squared plus b squared, where c is the hypotenuse and a and b are the lengths of the other legs. So putting in the numbers, we get 25 squared equals a squared plus 7 squared. That's 625 equals a squared plus 49. That's an equation. We know that we subtract the 49 from both sides. We get a squared equals 576. Now, because the a represents a length, it will be a positive value, and so the positive square root of 576 is 24, so a is 24. So the length of the missing leg is 24 centimeters. Therefore, the perimeter of the triangle is 7 plus 25 plus 24, that's 56 centimeters, and the area of the triangle is a half times 24 times 7, that's 84 square centimetres. Example 4. Robert is looking to buy a new television to put in a space that is 45 inches wide and 35 inches high. Could a full screen or a widescreen 54-inch television fit in this space? Let's consider first the full screen, and we know that the aspect ratio for the full screen is 4:3. So let 4x represent the width and 3x the height in inches. And since Robert's looking for a 54-inch screen, the length of the diagonal of the screen will be 54 inches. So on the imaginary right triangle that we have on the screen, the hypotenuse is 54 inches and the two legs are 4x inches and 3x inches respectively. Since it's a right triangle, we can use the Pythagorean theorem, and that is 4x all squared plus 3x all squared equals 54 squared. That will all come down to x squared equals 2,916 over 25, and we take the positive square root because the 4x and the 3x must be positive values because they represent lengths, and therefore that makes the x a positive value. So x comes out to be the positive square root of 2,916 over 25, and that comes out to exactly 10.8. Therefore, the width is 4x, which is 4 times 10.8, which is 43.2 inches, and the height is 3x, which is 3 times 10.8, which is 32.4 inches. But the available space is 45 inches by 35 inches. Therefore, a full-screen television will fit, and Robert can safely buy a full-screen television. You remember that the widescreen had aspect ratio 16:9. So let 16y represent the width and 9y the height of the screen in inches. Now again, the screen is a 54-inch screen, so that's the length of the diagonal of the screen. So if we imagine again the right triangle on the screen, the hypotenuse will be 54 inches, but the lengths of the two legs will be 16y and 9y inches respectively. And using the Pythagorean theorem, we'll get 16y all squared plus 9y all squared equals 54 squared. Now I'll leave you to do the calculations and work out the value of y. The width, therefore, will be 16y, and that's 16 times 2.94 ... That's approximately 47.1 inches. And the height is 9y, which is 9 times 2.94 ... And that's approximately 26.5 inches. So while the height of the television will fit in the space, the width of the television is too big. Robert should not buy a widescreen television. So by doing the maths, Robert will end up making the right decision as to which television he can buy. Consider the following situation. We have two squares, square 1 and square 2, and we're going to cut them up in different ways. Square 1 will cut up into 5 pieces. 4 of them will be congruent right triangles with legs A and B and hypotenuse C. And the 5th piece will be a smaller square of side length C. We'll cut square 2 up into 4 pieces. 2 of those pieces will be squares, one with side length A and the other with side length B, and the remaining 2 pieces will be 2 congruent rectangles with length A and breadth B. You would have noticed that square 1 and square 2 have the same side length of a plus b, so their areas are the same. You would have also noticed that the four congruent right triangles in square 1 fit together perfectly in the two rectangles in square 2. We are going to make use of all these observations to help us explain why the Pythagorean theorem works. All theorems need to be proved, so let's have a look at the proof of the Pythagorean theorem. The area of square 1, well, we'll call that A1, and it's made up of an area of a smaller square, which the area is c squared, plus the area of four congruent right triangles, each of which has area a half AB. So A1 will be c squared plus 4 times a half AB, that's c squared plus 2AB. Now in square 2, its area, which we'll call A2, it's made up of the area of the smaller square of side A, so its area is A squared, and area of a bigger square of side length B, so its area was B squared, plus the areas of two congruent rectangles, each of which has area AB. So A2 therefore is A squared plus B squared plus 2AB. Now both squares have the same area, so the two expressions must be equal. Therefore c squared plus 2ab equals a squared plus b squared plus 2ab. We subtract the 2ab from both sides and we get c squared equals a squared plus b squared, and that's the algebraic expression of the Pythagorean theorem. In logic, a conditional statement has the form if P then Q, where P and Q are statements. For example, if P is the statement it is raining and Q is the statement I catch the bus, then the statement if P then Q becomes if it is raining then I catch the bus. Now the Pythagorean theorem is one of these conditional statements. It could be rewritten as if a triangle has a right angle, then the sum of the squares of the two shorter side lengths is equal to the square of the longest side length. Now, sometimes we switch the two statements P and Q around, and therefore we get what's called the converse of the original statement. So the definition of the converse is given the statement if P then Q, the converse is if Q then P. The converse of our previous example is, if I catch the bus, then it is raining. Can you state the converse of the Pythagorean theorem? You would have said, in a triangle, if the square of the longest side is equal to the sum of the squares of the two shorter sides, then the triangle is a right triangle. For many theorems, their converses are true, but many other theorems have their converses which are false. Is the converse of the Pythagorean theorem true or false? Did you notice that when the area of the square on the longest side length of triangle ABC is equal to the sum of the areas of the squares of the two shorter side lengths, angle C is exactly 90 degrees? And that when the area on the longest side of the triangle is less than the sum of the areas of the squares on the two shorter side lengths, angle C is less than 90 degrees. And that when the area on the square of the longest side of the triangle is greater than the sum of the squares on the two shorter side lengths, angle C is greater than 90 degrees. In the Explore This 3 activity, we have a demonstration but not a proof that the converse of the Pythagorean theorem is true. We will not give the proof here. We will state the converse of the Pythagorean theorem again. In a triangle, if the square of the longest side is equal to the sum of the squares of the two shorter sides, then the triangle is a right triangle. Let us see how the converse of the Pythagorean theorem can determine whether a triangle is a right triangle or not. So, in the first case, consider the triangle shown with its side measurements. Is it a right triangle or not? Well, the square on the longest side is 52 squared, and that comes out to 2,704. The sum of the squares on the two legs is 21 squared plus 48 squared, and that will all come out to 2,745. And so those numbers are not the same. So by the converse of the Pythagorean theorem, the triangle is not a right triangle. For the second case, let's consider the triangle shown with its side measurements. Is this triangle a right triangle or not? Well, again, the square on the longest side is 85 squared, which is 7,225. The sum of the squares on the two legs is 13 squared plus 84 squared. That works out to 7,225 as well. So these numbers are equal. Hence, by the converse of the Pythagorean theorem, this triangle